Cables and conductors are an important part of electrical maintenance. If they do not match the requirements of the circuit in which they're installed, personal injury or equipment damage may result. In this part, we'll look at conductors and see how they're constructed. Let's start by defining two terms, conductor and insulation. A conductor is a material that provides for the easy flow of electrical current. Although electrical current can flow through most materials, it flows most easily through metals such as copper and aluminum. In this unit, we'll use the term conductor to refer to a metal wire that provides a path for the easy flow of current. Insulation is a material that is a poor conductor of electrical current. Materials such as rubber are highly resistant to the flow of current, so they make good insulators. Now let's see how conductors can be constructed. Conductors can be either solid or stranded, and they can be either bare or insulated. A solid conductor is a single strand of wire. A stranded conductor consists of several strands of wire wound together to form a single conductor. Stranded conductors are more flexible and easier to manipulate than solid conductors that are roughly the same size. Stranded conductors are typically used in situations such as conduit installations and control panels, where conductors sometimes need to be bent or bundled. A bare conductor is a length of solid or stranded metal wire with no insulation or cover. An insulated conductor is a bare conductor surrounded by an insulating material such as synthetic rubber or natural rubber. A conductor's insulation confines current flow to the conductor's wire and also helps protect the wire from mechanical damage such as nicks and scratches. In general, the thicker a conductor's insulation, the more voltage the conductor can handle. Some insulated conductors have an outer layer called a jacket. A jacket provides additional mechanical protection for the conductor and its insulation. Jackets, which are frequently made of hard plastic, are common on conductors that must be pulled through conduit. The jacket protects the wire and the insulation from mechanical damage that could be caused by sharp edges on the conduit. Sometimes, two or more insulated conductors are bundled together in the same jacket. We'll refer to this arrangement as a cable. Cables may be either solid or stranded. Cables are described by the number and the size of the conductors they contain. The American Wire Gauge, or AWG, is a system that's used to indicate wire sizes. This, for example, is a 3-conductor 6 AWG cable. It looks very different from this 49-conductor 19 AWG cable. Cables are convenient because you can install just one cable instead of several conductors. The terms conductor and cable are often used interchangeably. To avoid miscommunication, make sure that you understand how the terms are used at your facility. The conductors that we've discussed so far are typical low-voltage conductors. That is, conductors that are built to handle up to about 2,000 volts. Conductors that are built to handle over 2,000 volts are constructed differently. That's because they rely on design factors in addition to the thickness of the insulation to handle high voltages. In this unit, we'll focus on low-voltage conductors. That is, on conductors that are designed to carry less than 2,000 volts. Take a minute now to try a question about conductor construction. A conductor's insulation confines current flow to the conductor's wire and also helps protect the wire from mechanical damage, such as nicks and scratches. In general, the thicker a conductor's insulation, the more voltage the conductor can handle. Some insulated conductors have an outer layer called a jacket. A jacket provides additional mechanical protection for the conductor and its insulation. Jackets, which are frequently made of hard plastic, are common on conductors that must be pulled through conduit. The jacket protects the wire and the insulation from mechanical damage that could be caused by sharp edges on the conduit. Sometimes, two or more insulated conductors are bundled together in the same jacket. We'll refer to this arrangement as a cable. Cables may be either solid or stranded. Cables are described by the number and the size of the conductors they contain. The American Wire Gauge, or AWG, is a system that's used to indicate wire sizes. This, for example, is a 3-conductor 6 AWG cable. It looks very different from this 49 conductor 19 AWG cable. Cables are convenient because you can install just one cable instead of several conductors. The terms conductor and cable are often used interchangeably. To avoid miscommunication, make sure that you understand how the terms are used at your facility. The conductors that we've discussed so far are typical low-voltage conductors. That is, conductors that are built to handle up to about 2,000 volts. Conductors that are built to handle over 2,000 volts are constructed differently. That's because they rely on design factors in addition to the thickness of the insulation to handle high voltages. In this unit, we'll focus on low-voltage conductors. That is, on conductors that are designed to carry less than 2,000 volts. In this part, we'll examine factors that affect the classifications and ratings of conductors. Classifications and ratings are based on physical characteristics. These characteristics are the size and composition of the wire and the thickness and composition of the insulation. Let's first look at wire size. The term wire size is used to refer to the diameter of a solid or stranded conductor, and wire size is one way that conductors are classified. There are two systems commonly used to indicate wire size: the American wire gauge system and the circular mill system. The American wire gauge, or AWG system, is most often used to classify wires used in routine electrical work. AWG sizes range from 40 to 4/0, with 40 being the smallest. In this system, the larger the wire, the smaller the number. So 4/0 is the largest wire that can be classified by AWG size. Wires larger than 4/0 AWG are sized by the circular mill system. A mill is 1/1000th of an inch, and a circular mill is a circle that has a diameter of 1 mil. Sizes in the circular mill system range from 250,000 circular mills, abbreviated 250 kc mil, up to 2 million circular mills, abbreviated 2,000 kc mil. You may also see circular mills abbreviated MCM. This conductor, marked 250 MCM, could just as accurately be labeled 250 kc mil. A 250,000 circular mill wire has an area equal to that of 250,000 circular mills. This system uses actual measurements, so the larger the number, the larger the wire. The size of a wire affects the amount of current that it can carry. In general, the larger the diameter of a wire, the more current it can carry. But materials vary in their current carrying capability, so the composition of a wire, that is to say the type of material that the wire is made of, also affects the amount of current that it can carry. Together, the size of a wire and its composition determine how much current it can carry. The amount of current that a wire can carry without overheating is called its ampacity. If you double the size of a wire, you also double its ampacity. On the other hand, two wires that are the same size but made of different materials will not necessarily have the same ampacity. The maximum amount of current that an insulated conductor can carry without overheating is called its allowable ampacity. In addition to wire size and composition, a conductor's allowable ampacity is also affected by its insulation. That's because it usually takes less heat to damage insulation than it does to overheat a wire. So an insulated conductor would overheat at a lower temperature than the same conductor would without insulation. A conductor's allowable ampacity is a rating that can be found in the National Electric Code, or NEC, and in electrical handbooks. For example, this 4AWG copper conductor, with insulation identified as type RHW, has an allowable ampacity rating of 140 amps. Exceeding a conductor's allowable ampacity will cause the insulation to overheat and fail. This can cause personal injury or equipment damage. So it's important for a conductor's allowable ampacity to be equal to or greater than the amount of current in the circuit you're going to install it in. In addition to affecting the allowable ampacity of a conductor, insulation also affects a conductor's voltage rating. A conductor's voltage rating is the amount of voltage that the conductor can handle without its insulation breaking down. In general, the thicker a conductor's insulation, the higher its voltage rating. But insulation materials vary in their ability to insulate. So both the thickness and the composition of a conductor's insulation affect the conductor's voltage rating. The NEC requires that voltage ratings be stamped on the outside of conductors. For example, this conductor has a voltage rating of 600 volts. Exceeding a conductor's voltage rating will damage the insulation and eventually cause the conductor to fail. It's important to make sure that a conductor's voltage rating is equal to or greater than the voltage of the circuit in which it's installed. Different types of insulating materials provide different types of environmental protection, so conductors are also classified by insulation type. For example, some types of insulation are designed for dry environments and may tend to rot when they're exposed to high amounts of moisture. On the other hand, the types of insulation that are constructed to hold up under high humidity may tend to dry up, crack, and peel in an extremely dry environment. The NEC requires a letter code designating the type of insulation to be stamped on the outside of conductors. Letter codes represent specific types of insulation that are designed to hold up under specific environmental conditions. In this part, we've seen how the physical characteristics of wire and of insulation affect a conductor's allowable ampacity and voltage rating. We've also seen that conductors can be classified by the size of their wires and by the type of their insulation. Take some time now to try a question on this material. In this part, we've seen how the physical characteristics of wire and of insulation affect a conductor's allowable ampacity and voltage rating. We've also seen that conductors can be classified by the size of their wires and by the type of their insulation. In this topic, we've talked about the basic construction of a conductor and about how conductors can be classified and rated. Take some time now to try these practice questions. In this part, we'll examine characteristics of a circuit that affect the types of conductors that should be installed. We'll see how to determine the current requirements and the voltage requirements of a circuit. Every circuit has basic current and voltage requirements that are determined by the equipment that's connected to the circuit. Identifying these basic requirements is sometimes as simple as reading the information directly from an equipment nameplate. In other situations, you may need to refer to manuals or maintenance materials that provide current and voltage information. The basic current requirement for a circuit is calculated by adding the individual current requirements for all of the equipment that's connected to the circuit. For example, a circuit with two 60-amp motors has a basic current requirement of 120 amps. The rating that's used to describe the current carrying capability of a conductor is called allowable ampacity. Generally, the allowable ampacity of a conductor should match or exceed the basic current requirements of the circuit in which it's installed. But there may be situations where a conductor's allowable ampacity should be higher than the basic current requirements of the circuit. One of those situations is a circuit that has a motor. Motors draw additional current when they first start up. To allow for this, the National Electrical Code, or NEC, requires conductors installed in circuits that include a motor to be rated to carry at least 125% of the motor's operating current. For example, let's assume that a circuit includes a motor with an operating current of 30 amps. According to NEC standards, a conductor installed in this circuit should be able to carry 125% of 30 amps. To find out how much current that is, we'll start by changing 125% to a decimal. Then we multiply 30 amps by 1.25 and get a total of 37.5 amps. So a conductor in this circuit should have an allowable ampacity rating of at least 37.5 amps. Our example was based on NEC standards, but local codes and facility standards may vary from the standards set by the NEC. Make sure that you know the specific electrical standards for your facility before you start any electrical work. When there's more than one motor in a circuit, the NEC requires the operating current of the motor drawing the most current to be adjusted by 125%. For example, let's assume that we're installing a conductor in a circuit that has a 15-amp motor and a 30-amp motor. To see how much current the conductor must be able to carry in order to meet NEC standards, we multiply 30 amps, the operating current of the motor that draws the most current, by 125%, or 1.25.